Hello, my dear students. How are you all? I think all of you fine. So today we will discuss about the chapter number 6, Electromagnetic Induction. So in this electromagnetic induction, today we will discuss about the mutual induction. So what is meant by the mutual induction? So mutual induction is the phenomenon of inducing EMF in the secondary coil due to the change in current in a primary coil, and hence the change in magnetic flux in the secondary coil. Suppose here the two coils are there, one is a primary coil, another one is secondary coil, and the primary coil and secondary coil are not connected each other. Okay, there will be no electrical connections using wires, there will be not connected. Okay, so the primary coil and secondary coil is nearer to each other. Okay, the distance between the primary coil and secondary coil is very small, but the electrical connection is not there in that two coils. After that, whenever the two coils are present, primary and secondary coil, then if the current in the secondary coil, okay, increases or decreases, then the current in the primary coil is also varies. Okay, so the mutual induction is what? It is the phenomenon of induction of EMF and hence current in the secondary coil due to the variation of current in the primary coil. Okay, so that is meant by mutual induction. Then after that, the mutual induction, suppose the phi to 1 is directly proportional to I1, where what is meant by phi to 1? So that is the magnetic flux linked with the secondary coil is directly proportional to current present in the primary coil. So if you will take proportionality sign to equal sign, you should take one constant. Therefore, the proportionality sign to equal sign. So phi to 1 is equal to m into I1, where m is the constant of proportionality and it is also known as mutual inductance, or it is also known as the coefficient of mutual induction. Coefficient of mutual induction. If I1 is equal to 1, then m is equal to phi. If I1 current in the primary coil is equal to 1 unit, then the coefficient of mutual induction is equal to phi. Thus, the mutual inductance is defined as the magnetic flux linked with the secondary coil when unit current flowing through the primary coil. When unit current flowing through the primary coil. So that is E2 is equal to minus d phi to 1 by dt. If E2 is equal to minus d phi to 1 by dt, or it is also E2 is equal to minus m di1 by dt. If di1 by dt is a 1 unit, okay, then the m is equal to E. So that only the mutual inductance is defined as the induced EMF set up in the secondary coil when the rate of change of current in the primary coil is unity. Okay, so that is what the mutual inductance is defined as the induced EMF set up in the secondary coil when the rate of change of current in primary coil is unity. So that is the SI unit of mutual inductance is Henry. Okay, and The mutual inductance is said to be 1 Henry when 1 ampere current in the primary coil links magnetic flux of 1 Weber across the secondary coil. Okay, so that is what the mutual inductance is said to be 1 Henry when 1 ampere current in the primary coil links magnetic flux of 1 Weber across the secondary coil. Or it is also defined as mutual inductance is said to be 1 Henry when unit rate of change of current is 1 ampere per second in primary coil induces EMF of 1 volt in a secondary coil. So the mutual inductance is said to be 1 Henry when unit rate of change of current is 1 ampere per second is primary coil and induces EMF of 1 volt in a secondary coil. Then we will see the one expression, that is the mutual inductance of a two long coaxial solenoids. Okay, so that is the expression for mutual inductance of two long coaxial solenoids. Suppose here the two solenoids are coaxial solenoids, okay, and both are having the same length. Both are having the same length. So suppose in this mutual inductance, okay, so we'll consider the two long air cored solenoids, okay, so here the two long solenoids and the each of length will be L, okay, both are having the same length as a L. The solenoid surrounds this and they are having the suppose the number of turns of the coil, okay, so the first solenoid, suppose A and P are the two solenoids, each of length L, and N1 is the number of turns of the solenoid and N of the first solenoid and N2 is the number of turns of the second solenoid. Then the flux leakage of the solenoid is directly proportional to current in the solenoid. Okay, the flux leakage of the solenoid is directly proportional to current in the solenoid. That is N1 phi1 is directly proportional to I2, where N1 is what? The number of turns of the first solenoid. Phi1 is what? The magnetic flux linked with the first solenoid, that is directly proportional to current in the second solenoid, I2. So therefore, we will write the proportionality sign to equal sign. If you will take, you should take the one constant. Suppose M12 is the one constant, or that is also known as coefficient of mutual inductance, and that is suppose the N1 phi1 is equal to M12 into I2. Therefore, what is meant by M12? M12 is equal to N1 phi1 divided by L2 divided by suppose I2, and the magnetic field due to the primary solenoid, suppose the magnetic field due to the primary solenoid is what? B1 mu naught N1 I1, B1 is equal to mu naught N1 I1. Therefore, the magnetic flux linked across the turns of the solenoid is, that is phi 2 1 per turn for each turn, okay, we'll find that is B1 into A, where the B1 is what? That is magnetic flux of the solenoid A, and after that the A1 is the, suppose, the area, okay, area of the solenoid. Then after that, the suppose the phi to 1 per turn is equal to B1 into A. But what is the B1 value? That is mu naught N1 I1 into E. And that is equal to mu naught N1 I1 A by L. Okay. Whenever the, if we will take the N1, okay. If we will take the N1, suppose the N1 is what? The number of turns per unit length, and capital N1 is the total number of turns of the first solenoid. Okay, so after that we'll see the magnetic flux linked across the n turns of the secondary solenoid is phi to 1 is equal to mu naught n1 n2 I1 A by L. Okay, suppose the phi to 1 is a m21 into I1. So using this, what is m21? M21 value is mu naught n1 n2 A divided by L. Okay, so here that is I1 divided by I1. Okay, both I1 get cancelled. So therefore that is equal to, we will also write mu naught n1 n2 AI. Here the n1 n2 are the self, mutual inductance, okay, of the coaxial solenoids. Okay, that is the M mutual inductance of the coaxial solenoid. M21 is equal to mu naught N1 N2 A by L, or that is equal to mu naught N1 N2 A by A into I. Here the M12 and M21, okay, both are equal, okay, both are having equal expression. So therefore, for a two long coaxial solenoids of same length and same cross-sectional area, the mutual inductance is same and leads to principle of reciprocity. So that is what the M is equal to M12 and that is equal to M21. Okay, therefore the mutual inductance of a two long coaxial solenoids are having expression M12 is equal to mu naught N1 N2 A divided by L, or it is also equal to mu naught N1 N2 AI. Okay, and the both are having the same expression. So therefore M is equal to M12 is equal to M21. Okay, so this is the mutual inductance of two long coaxial solenoids. Here I repeat. So the two solenoids, okay, the two solenoids, they are having the coaxial solenoids and having the same length as a L, and the I amount of current is flowing in that solenoid, both solenoids, and I1 is the current of the first solenoid, I2 is the current of the second solenoid, N1 is the number of turns of the first solenoid, N2 is the number of turns of the second solenoid. Therefore, The flux leakage of the solenoid is directly proportional to current in the solenoid. Therefore, N1 is directly proportional to I2. So that is, the flux leakage is directly proportional to current in the secondary solenoid I2. So therefore, N1 is equal to M12 into I2, where M12 is what? It is the coefficient of mutual inductance. Therefore, M12 is equal to N1 divided by I2. Due to the primary solenoid, the magnetic field will be B1 is equal to mu naught N1 I1, and the magnetic flux linked across the turns of the secondary solenoid is 5 to 1 per turn is equal to B1A, that is equal to mu naught N1 I1 A, and that equal to mu naught N1 I1 A by L. Then the magnetic flux linked across the n turns of the secondary solenoid is 5 to 1 is equal to mu naught N1 N2 I1 A by L, but 5 to 1 is equal to M21 I1, and that is the M21 is equal to mu naught N1 N2 A by L, or that equal to mu naught N1 N2 A A. Okay, so this is the expression for mutual inductance of two coaxial solenoids, and that is, suppose the M12 is equal to mu naught N1 N2 A by L, or that is equal to mu naught N1 N2 A by A into I. Suppose here the M12 and M21 value will be same. Okay, so because of that, for a two long coaxial solenoid, the same length and same cross-sectional area, the mutual inductance is same and leads to the principle of reciprocity. So that is M is equal to M12 is equal to M21. Okay, here this is the expression. Okay, so after that we'll see the some additional information, okay, about this chapter. Suppose if the two solenoids are wound on a magnetic core of relative permeability mu r, then mu naught mu r n1 n2 A by L. Okay, then expression will be what? Mu naught mu r n1 n2 A by L. If the solenoids S1 and S2 have number of turns of coil N1 and N2 of different radii R1 and R2, then the expression for M is equal to mutual inductance is equal to mu naught mu R N1 N2 pi R1 2 divided by I. And the mutual inductance depends also on the relative placements of the solenoids. Okay, it is also depends on the relative placements of the solenoids. The effect okay, the coefficient of coupling K. Okay, K is what? The coefficients of the coupling between the two coils having the self inductance L1 and L2, and mutual inductance M is K is equal to M divided by root of L1 into L2. Generally, whenever the K is less than 1, if L1 and L2 are the series, then L is equal to L1 plus L2, and if L1 and L2 are the parallel, then the 1 by L is equal to 1 by L1 plus 1 by L2. Thank you.